So, round robin algorithm basically works with respect to this time quantum. Every process will be given a particular time slice, and this time slice is the maximum amount of time that any process can enjoy and can complete its execution within the given time quantum. Otherwise, it has to go through multiple time quantums for run to its completion. Right? Now, here we have seen time quantum can be big or it can be small, then different applications will happen. If it is large, then there will be less overhead of context switching. If the time quantum is less, then there will be more context switching. So, more overhead. Now, let us do what are the different values for this q. Hold on, what happens if q is infinity? Now, let us assume that for a process to execute, okay, first the process has to change, the processor has to change the context to load the information about a process. Suppose the time which is taken by this process is s, it's a context switch time, and assume that t is the amount of time which is taken by this process to run. Okay, t is the amount of time it takes. Now, this is actually the total time. Now, what happens if this time quantum is actually the total time which is taken by the process, the amount of time it requires actually plus context switch time. So, what happens if q is infinity? Then a process can be executed in a single shot. So, it is nothing but first come first serve, FCFS algorithm. Now, here we will find out for different values of q what is the CPU utilization. CPU utilization. Now, the CPU utilization can be found by just considering how much amount of time it has actually spent in execution. Okay. Amount of time spent for actual execution. Here actual total time is s plus t, but actually it is executing for t amount of time, okay, by total time. Okay. So, when q is infinity, then the amount of time the CPU utilization will be the actual time it takes by the total time s plus this context switch time. Q is assume that q is the time quantum. Q is the time quantum, okay, and S is context switch time. So, this will be the CPU utilization. Now, if the value of q is less than t, what happens? If the value of q is less than the amount of time the process actually needs to run to its completion, then then the CPU utilization in this case will be, so actually whatever, if the amount of time the process requires is t, but this t is greater than q, then actual time spent by the process in executing is q only, because as I have told that time quantum is the maximum amount of time which is enjoyed by any process for execution. So, if the amount of actual amount of time required by the process is t, which is far greater than q, then no process will be allowed more than q times to execute. So, actual amount of time which is spent is q in case of if q is less than t, but the total amount of time is q plus t, s plus t. So, this is the CPU utilization in this case if q is less than t. Now, what happens if CPU if the value of q is infinity, we have seen. Okay, what happens if the value of q is greater than t? If the value of q is greater than t, then of course it will run for q amount of time. Here we take care that this time quantum should also be less than context switch time, should be greater than context switch time. Then here in this case as well, amount of time, the CPU utilization will be the actual amount of time spent is q, of course, because q is greater than t, and total amount of time is context switch time plus q. Okay. Q. Okay. Now, what happens if q is 0? If q is 0, then the CPU utilization is 0 by whatever it is. You will get 0. It means there will be no progress, no process can execute because time quantum is 0. So these are the different cases what happens when the value of q changes. Now we'll do one problem, a simple problem on this round robin analysis. So I think I have question with me. Okay, question is, consider n processes sharing the CPU in a round robin fashion assuming that each process switch takes s seconds, what must be time quantum q such that overhead resulting from process switching is minimized but the condition is at the same time each process is guaranteed to get its turn at the CPU at least every t seconds. Okay. We have a system having n processes sharing the CPU. We have only one CPU. We are talking about uniprocessor scheduling here. In a round robin fashion, assuming each process switch takes s seconds, s is the context switch time. So what must be the time quantum q such that overhead resulting from processes switching is minimized, but at the same time each process is guaranteed to get its turn at the CPU at every t seconds. This t seconds. Now let us assume that it's actually given that there are n number of processes. Now if there are n number of processes, now if I draw a timeline, okay, now assume that first process P1 is executing and process P1 is executing. Now it will execute for a maximum of given time quantum q. Now afterwards it undergoes time context switching s. Okay. Now, after this another process, assume that P2 will be selected, and it will also be executed for given time quantum. Okay. Now, actually he has given multiple choices here. Okay. Is the value is A, Q is greater than or equal to T minus ns by n plus 1, or Q is greater than or equal to T minus ns by n minus 1, C Q is less than equal to T minus ns by n plus 1, or Q is less than T minus ns by n plus 1. Okay, what be the value of Q in order to avoid context switch overhead, so that process switching is minimized. Then another process, P2 will be given chance. Before it is given chance, again context switch happens, as then another process P3 will be given chance. It will also be executed for time quantum, and another context switch happens. Then so assume another process goes, takes, so on up to n number of processes. Okay. So now when first process P1 is executed, then the turn of this process will come after. Now let's assume instead of n, we will take n is equal to 4 here, for example. If n is equal to 4, then I have 4 processes, for example. Then if process P1 is executed, then the next time interval in which again process P1 turn comes, okay, will be T. That it's a turn that the CPU at least every T seconds a process should get chance to execute. So this process P1, after this T seconds it gets chance. For this process P2, this T starts from here, then process P2 has to get some chance for execution. So this is T. Then how do we minimize the context switch? It means I want to minimize this context switch times. So for n is equal to 4, then what would be the time quantum? Okay. In order to minimize this, assume this is the total time T, or I'll call it T. So and then what do we do is we take this T seconds, okay, minus how many number of processes are there? Process 1, 2, 3, 4. 1, 2, 3. Only 3 processes are there. Okay. So, but I have to minimize the overhead, context switch overhead. There are 3 processes, but how many context switches are there? 1, 2, 1, 2, 3. Okay. Now, one more important thing is, again it takes context switch here for loading this process. Okay. So actually how many number of context switches are there? Ns. So total number of processes are n, so 4 times this context switches into S. Okay. By total number of processes in this range, or excluding this P1, we have P2, P3, P4, which is only 3. Okay. So the time quantum should it should be either less than or equal to this value in order to minimize the overhead. So now let's generalize this formula. So we take it as Q should be less than or equal to T minus n into S by n minus 1. So in order to minimize the context switch overhead, the value of time quantum should be less than or equal to T minus n into S by n minus 1. So Next, we have already talked about this priority scheduling algorithm, right? Now, what actually the Unix operating system, the traditional Unix operating system doesn't uses any specific algorithm. It uses a mix of many algorithms. For example, the traditional Unix operating system, it uses round robin multi-level feedback with priority queues. Round robin multi-level feedback priority queue. This is the algorithm which is followed by traditional Unix system. Now here, how this priority will be calculated? So priority, what do you mean by this multi-level feedback? There are actually another class of algorithms called multi-level scheduling algorithms and multi-level feedback scheduling algorithms. Now let us talk what is the difference between them, or first let us see what is multi-level priority scheduling algorithm or multi-level scheduling algorithm. In multi-level scheduling algorithm, processes are, each and every processes are divided into different classes, okay, depending upon their type. So depending upon the type of processes, each and every process has been classified, and according to this classification, for each and every classification we will have one queue. Okay. Now the resulting mechanism would be, there will be one level of queue. Okay, this queue will have one highest priority. Then you have some another queue. Then here you will have some priority which is associated with this queue. It means all the processes which comes to this queue will have certain level of priority. Then similarly you go on having different level of priorities. Now assume that this is low priority, this is mid priority. Okay, and this is the highest priority. And CPU, whenever any process comes, okay, depending upon the classification, this process will be sent to a different queue. Suppose if a process comes at priority queue, at highest priority queue, then all this, from all those processes which are there in low priority queue and mid priority queue, okay, process P1 will be given priority first. Okay. So P1 will be executed first. Now a question arises, when process P2 which is there in mid priority queue will be executed. It is executed if and only if the highest level priority queue is empty. Okay. If this is empty, then only the process then only the scheduler will take any one of this process from the mid priority. So when a process takes a process, suppose which is P3 which is in low priority queue, it takes only if the highest priority and the mid priority queues have been completed or they are empty, then only the chance will come for this lower priority. But there is one problem with this. The problem is starvation again. Okay? There is a possibility of starvation. Now what happens is, assume that there is one process which is running and there is another process which is waiting here. While this process is executing, another process came. When this process P2 is executing, another process came. Okay, this P5, P6. Now there is a possibility that all the processes with highest priority or mid priority go on coming, thereby leaving all the processes at the low priority queue into starvation. So it is possible for all these processes which belongs to low priority queue to execute if and only if the high priority queues are empty. So this leaves the system in a starvation. Here we cannot apply aging. Why? If you apply aging, then it increases the priority. It increases the priority, then the process has to be shifted from low priority queue to mid priority, from mid priority to high priority. But in multi-level scheduling algorithm, you don't have any concept of moving any process across the queues. If a process is classified into low priority, till it gets it's done from a scheduler, it doesn't move to another queue. It will be, till its end, it will be at low priority queue only. If a process is classified at higher priority, then it will be till its end or till it has completed its execution, it will be in higher priority queue only. Okay. So this is the problem with this multi-scheduling algorithm. Now, in order to accommodate, in order to overcome this starvation, okay, there are few improvements have been done on multi-level scheduling algorithm. Okay, but that is what we call it as multi-level feedback scheduling algorithm. Multi-level feedback scheduling algorithm. So, what is this multi-level feedback scheduling algorithm? Here there is a provision of moving one process, okay, that a process which belongs to one priority queue can move to another level of priority. A mid priority process can move to a higher level priority process. So, the concept of aging will work here. So, in multi-level feedback queue, the feedback, the meaning it has been included here because it is possible to move processes from across the queues. But here in this algorithm, we need to take two scheduling decisions. Okay, the first scheduling decision is for which process has to be given chance for executing, and another is we have this many number of queues available, ready queues available. So, we have to schedule which queue has to be given priority to be executed. Now, in order to overcome this, we use a round robin algorithm for. So, the better refinements over this would be if you have a round robin algorithm which is implemented, it means a particular time will be given for each and every queue, and in the duration of time the scheduler has to take decision to select any one of these processes depending upon the specific algorithm which is followed at this level. For example, at the round robin algorithm is used for selecting any one of this ready queue. Okay, suppose the highest priority ready queue has been selected, then which algorithm are you using here? Okay, it might be again round robin algorithm. If you are going here, you might be using some priority algorithm. Okay, if the ready queue, if the time quantum is given to this queue, then this queue might be following some FCFS. Okay, so it depends. So, what type of algorithm you want to follow each and every queue, okay, might differ from ready queue to ready queue, and generally it's a good idea to have a round robin algorithm for selecting any one of these ready queues. Okay, and when we have this round robin plus concept of aging, okay, then it may solve the problem of starvation, because a process if the number of if it goes on increasing its age, then there is possibility for this process to move to the higher priority ready queues. Okay. This is called multi-level feedback queue scheduling algorithm. So, actually we started it from here. The Unix operating system follows round robin multi-level feedback priority queue. So, here how this priority is calculated. Now, this priority is calculated depending upon the type of the process and a past history. So, to give if I were asked to write a mathematical equation that how generally it gets calculated, let us first talk about this terminology. So, you have a CPU, the process J for example is running on CPU in a time interval I, okay. Then the maximum CPU utilization by this process J in time interval I can be calculated by its past history I minus 1th interval by this process G with some constant K. We have some constant here, so I am writing here 2. So, this is the maximum CPU utilization, it is the processor utilization of process J in time interval I, okay, and this gives you this is the past processor utilization divided by some constant. Okay. Now, actually the priority for this algorithm round robin multi-level feedback multi-level priority queue algorithm, feedback priority queue, it is calculated every process when it is submitted to a system, they have some base priority. So, suppose process Pj has some base priority base j, okay, then that will be added with this estimated CPU j of I minus 1 by 2. It means depending upon the past history, in order to calculate the priority of a process, the base priority will also be considered, plus its past processor utilization, plus some value called nice value will be given. This is actually user controllable factor, or user can control this priority by giving this nice number. Now generally in Unix, less the value of this priority means the process will have higher priority. If the number is less, priority number is less, then higher priority will be given to this process. Okay. If the priority number is high, then low priority will be given to this process. Okay. So by this we have completed this all priority scheduling algorithms. But there is one thought-provoking question which we would like to do here, which thereby will conclude this scheduling algorithm topic, and then start mutual exclusion. So let me give one question I have with me. Okay. At a single terminal CPU, if 40% of all the users have no weight to use the terminal, and average wait time for all users is 50 minutes, then what is the average waiting time for those who wait? Okay. Few options have been given, 60, 70, 80, A, B, C, D. It's 90. Okay. Now let's find. This is at a single terminal CPU, if 40% of all the users have no way to use the terminal, and average waiting time for all the users is 50 minutes, then what is the average waiting time for those who wait? Now generally assume that we have n number of users, which want to assume that we have n number of users who want to use the single terminal CPU. Among this n number of processes, it has been given, the information has been given that 40% of the users they don't have to wait for using the terminal. So the waiting time for this process for 40% of the users is 0. Now let us find out what is the formula for average waiting time. The formula for average waiting time is waiting time for process 1, okay, plus waiting time for process 2, plus waiting time for process 3, so on, waiting time for process n by total number of processes, which is n. Okay. Now it has been given that 40% of the processes out of n, meaning what is the 40%? 0.4 n number of the processes or number of users has to should not wait. They don't have to wait for accessing a terminal, and remaining of them, which is 60% of them, have to wait some amount of time. But together with this 40 and 60%, the total amount of average waiting time has come up to 50 minutes. It means this 50 minutes has been taken by all of this. Okay. But here we have divided this process into two categories. 40% of the processes, okay, waiting time 1 plus waiting time 2 up to 0.4 n. Okay, all of this process has to wait for some amount of time. How much? Assume that the amount of time they have to wait is x1 plus now remaining processes, which is waiting time 1, waiting time 2 up to 0.6 n of this process have to wait for x2 amount of time, okay, and n. So 40% of the processes are waiting. So 40% of the processes are waiting x1 units of time, and remaining 60% of the processes, they are waiting for x2 amount of time. Okay. And the average of them is 50 minutes. But it has been given that 40% of the users, they need not wait, for accessing the terminal. So x1 is given as 0. When x1 is given as 0, then I have to find out x2. Okay. And the average waiting for time for those who wait. Okay. So it means I have to first find out the value of x2 and I have to find out the average for the 60%. Okay. So let's substitute the value of x1 here. So 50 minutes gives me 0 plus 0.6 n by n into x2. So n gets x2 will be how much? 500 by 6. Okay. So the amount of time they have to wait is 500 by 6. Now if we take average of this, so which is equivalent to, okay, now we have got the value of x2 here. So let's find out the average waiting time for 60% of the processes. So yeah, we got that when we divided this by 60, we get some 83.3. Yeah, the answer is this C. However, but now we'll do one step ahead. What do we do is we'll find out the average waiting time for what is the average waiting time of only this number of processes, because they are waiting no time. They take zero amount of time. 40% of the process take 0 amount of time. So what do we do is 50 minutes. Okay, we'll take like this 0.6 n x2 by this many number of processes wait. Okay, how much? N minus total number of processes will be 0.6 n. Okay, so this will be total average waiting time for 60% of the processes. So we know that the value of 0.6 n into x2 value we know already, which is 500 by 6. Okay, by this is how much? Total number of processes will be 60% of the process. How do you find out average? Total number 60% of the process by 60% of total number of processes will be 60. Okay, 60%. So n minus 60% is 0.4. N minus 40% will give us 60%. Okay, so again it will be 0.6 n again. Okay, so this gets calculated. Again we have got the same value 500 by 6. Okay, so average waiting time. The average waiting time for those who wait. Okay, they are the process those who wait actually. Also we got the same value, which is 83 point something we will get. Okay, so C is correct. So this is what about different scheduling algorithms. Now we will start another topic called mutual exclusion. Before we go into mutual exclusion, let's talk about how do we create a process, and how this process going to create inconsistency, all these things we'll see now. So far we discussed about that process has to be created. How this process will be created? Process can be created with the help of a system call called fork. Fork is a system call which creates a process. Okay. Now, what is this? What is the difference between a system call and a library call? Now, what is system call and what is function call? Function call is generally made by a user, and the function is written by the user itself. It means at user mode. Generally, you take an example of C programs. We write sum, average. Okay, these are the functions which are written by us. These are called user functions. Okay, when we call these functions, we call it as a function call. But what do you mean by system call? System call is also a function, but it's a special kind of function. Okay, your operating system is actually it is a set of services, and all these set of services are available to the user in the form of system calls. So, system call is a mechanism via which a user requests the services of an operating system. Okay. So, whenever we execute a system call, or whenever a system call is executed, the control goes into the kernel mode. Control goes to the kernel mode, but for a library call, control remains in the user mode. As we know that operating system works in two modes. Okay. One you have user mode, and another you have kernel mode. Okay. All the processes will be user processes will be running in the user mode, and all the system processes will be running in the kernel mode. System call is a service requested from the operating system. So it is nothing but whenever a system call is executed, an interrupt will be generated, right? And this is called a software interrupt. Okay. This software interrupt goes to whenever there is a software interrupt. Okay, and then the dispatch table will be looked into. Here you will have ISR, interrupt service routines, and this will be serviced, and thereby the user gets the service from the operating system. Now, whenever control moves from user mode to kernel mode, okay, there is one register called PSW. Program status word. Okay. Now, the value of this program status word can be 0 or 1. If the value of PSW is 0, it means it's in kernel mode. Kernel mode. 1 means it is in user mode. Now, I'm in confusion whether it's 0 means in user mode or kernel mode. But one value for PSW, okay, it's in user mode, and another is in kernel mode. But in order to access this, in order to access the value of PSW, we cannot access this register from user mode. Okay, so of course we have to make help of system calls. So whenever a system call is executed, the value of PSW will be changed, and the control will be jumped into the kernel mode. Now, after getting the service, again the last instruction in the system call, we also call it as a supervisory call, is again a system call which will change the value of PSW to earlier value, which actually signifies that the control is in user mode. Okay. So that is basically the difference between them. And there is one more thing called trap and interrupt. Okay. Trap is generally used for it is generally used for representing erroneous condition, some error, but whereas interrupt, it's like it is nothing but attention of operating system or the CPU is being gained. Generally, it is these are generally generated by the software. Okay, they are software interrupts. Okay, trap can be hardware interrupts. So whenever you do a fork system call, it means fork is a system call. It requests services from the operating system, which is a request to create a new child process. So a child process will be created. Once a child process gets created, that child process will have all the resources which are held by the parent. So this is the parent. Suppose if it has executed a fork system call, okay, it gives birth to child process. This child process will have exact, it has all the resources which are there with this parent process will all be inherited by the child processes. Okay. Now how do you differentiate this? If the idea of this process here will be 0 and the idea of this parent process will be greater than 0. So there is the way in which parent and the child process can be differentiated. Now if I have written this program for do nothing loop, it is an infinite loop, and if I want to execute this fork system call, or before we suppose, don't try this on your system, it's called fork bumping. Suppose if I have written fork, I have written this void main, okay, and I have executed this fork system call once, and I have written printf hello. The output of this program is not hello, but hello will be printed 2 times. Why 2 times? One time is printed by the parent and another is printed by the child. Okay. So if I have written 2 times fork, then what happens? Then 4 times the printf will be executed. Okay. 3 times it will be printed by the children, and 1 time will be the parent. If there are n number of forks, for example here, so suppose if there are n number of fork system calls, then how many number of processes are getting created? Okay. If there are n number of fork statements, okay, then total number of processes that gets created are 2 power n, and total number of child processes that gets created are 2 power n minus 1. These are the child process, and including parent process, it will be 2 power n. So this is total number of processes, and this total number of child processes that gets created. Okay. So now this the output may vary from operating system to operating systems. Okay. Few operating system may doesn't allow you for to a particular limit that you cannot go on creating the process. Few may allow you, resulting in a fork bumping, and entire memory will be exhausted and there will be no memory existing for creating a new process. So the behavior may changes from operating system to operating system. Okay. So now when there are multiple processes which are created in a system, and all of this process if this processes, okay, like using fork system call, we can have a child and parent relationship. It is also possible to create a process in which there is no any relationship which is existing. Like fork will create a child parent, and both of them can communicate because they are having a child and parent relationship. It is also possible for 2 processes to communicate. Okay. How they can communicate? Either they can communicate with the help of passing messages, or they can use message queues. Okay. And this one process want to communicate with another process P2, it sends one message to the message queue, another process will read from the message queue, or they can use pipes, they can use shared variable or shared memories, okay, for communication, or our process can communicate with the help of their IDs as well. So there are many ways in which 2 processes can communicate. So when these 2 processes are communicating, and if there is any resource which is shared between them, then here the problem arises. Now let's imagine a situation wherein I have a process P1, I have another process P2. Okay. Now both of them are executing simultaneously. Assume that we have a uniprocessor system, or let's take first for our convenience, we have a multiprocessor system. Okay. And there is one resource which is shared between them, for example A. Okay. Now the value of A is 10, and I want to execute. Now suppose this process P1 is incrementing the value of A by 1, A is equal to A plus 1, and this process is also increment the value of A by 1. But because it is shared, So when both of them trying to access this variable, both of them will see the value of a to be 10, and it will increment the value of a to be 11, and this will also increment the value of a will be 11. But now you see, just if I change the order of execution, okay, or instead of parallel execution, simultaneous or concurrently executing these two processes on two different processors, I'll allow first one process to execute first, then assume that if I have given chance for process P1, then process P1 will change the value of a to 11, and then another process P2, while when after this process P1 has completed its execution, when process P2 has been given chance, then process P2 will see the value 11. Why? Because this is a shared variable. So when it sees the value 11, then it increments the value to 12. But now with the observation what we did here is, when I am executing these two processes concurrently, I am getting one result. When I am executing them in a sequential order, okay, then it is giving me a different result. This is called inconsistency. How to get consistency? Consistency means irrespective of in which order I am executing, okay, either concurrently or sequentially, I should get same output. Okay, then the result is consistent. But for one kind of execution, sequential execution, I am getting one output, and for concurrent execution, if I am getting another output, then this is called inconsistency. Okay. So generally inconsistency, this will because now this inconsistency will give you bad result, and this actually we don't want this actually. The root cause for this here is the shared resource here. If this resource is not shared and it is local for them, then there would be no problem here. But the problem here is because it is shared, and I want it to be a shared, and still I want consistency, then we need to look for different synchronization mechanisms. Even if you change the architecture, if you take it as a uniprocessor system also, if you take a uniprocessor system, changing the architecture doesn't changes the problem. If you have a processor architecture or uniprocessor machine, now let's assume that. Okay. Now we know that as I have told you that interrupt can occur at any point of time. We cannot guarantee that interrupt should not occur at this point of time. Interrupt may occur at any point of time. So when assume that when a is equal to a plus 1 is executed by process P1, this is at higher level language seems to be a single instruction, but at machine level it has been splitted or broken down into multiple machine level instructions, right? So now assume that now how it will be executed. It will be executed like this. First the value of a will be loaded into R1. R1 assume that this is a register, and from memory the value of a will be loaded, and then it has been incremented. The value of R1 has been incremented. Then again I am storing the value of again I am storing the value of R1 in M. Okay. Now this is the sequence of instructions and machine level that gets executed. Now there is actually at higher level one instruction, but at lower level it has been split down into three different instructions, three different independent atomic instructions. So now what happens? Assume that when for this process P1, okay, I'm just naming it as 1, 2, 3. Okay. For process P1, instruction 1 has been executed. Okay. Initially the value of a assumes to be 10. Okay. So now in memory we'll have what? In register R1 it will have the value to be 10. And second is executed, then R1 will have value 11. Assume that here interrupt comes. Okay. When interrupt occurs, because it has not updated here, okay, it didn't stored. Okay. Now concurrent execution in uniprocessor system is nothing but process interleaving. Okay. When process interleaving happens, what happens here? When process P2 is executed, process P1 when process P2 gets executed, first instruction, okay, now when this first instruction is executed by this process, now this process sees the value still to be 10, it is not 11 because it has not been updated. So it sees the value to be 10, and also it also increment the value of 1 to be 11. Okay. Now here also it gets interruption. Okay. Now assume that here when it displays the value of R1, Okay, it updates the value of R1 to be 11, okay, and it also updates the value to be 11. But there are, in total, there are two number of increments, but as a result of concurrent, execution in a uniprocessor system by, pseudo parallelism or process interleaving, still I am having inconsistent result. Okay. The observation what we had is, if we change the architecture from uniprocessor system to multiprocessor system, it doesn't means that the problems of synchronization has been solved. No, it still persists. So we need some few synchronization primitives which solve these problems, okay, which we will see in the next class. So we will stop here.